well, welcome everybody to this webinar. Today we're going to be talking about electro-thermal analysis in EMS. The presenter is going to be Dr. Ahmed Saeed. This presentation should last in the neighborhood of 30 to 35 minutes. After that, we'll open the floor to questions. And please type your questions in the chat box right here. You can type your questions there. So once Dr. Ahmed is done with this presentation. So now I'm going to take the screen to Dr. Ahmed. And again, welcome everybody.
Now the idea here is to apply the convection to all the phases in the transformer and device that are they come in contact with external fluid or liquid or air. So, and again, as I said earlier, you could, in essence, apply each individual phase, but it's going to take a long time. So we said, okay, the whole environment could just select the parts that represent the environment, and then automatically it will apply the convection now. Okay, so you specify the convection coefficient as usual, and the ambient temperature. Okay, now let's talk about the limitation here. This is not going to replace your SolidWorks simulation where you have really a powerful thermal program or fluid there. We assume that the convection coefficient is constant for that surrounding liquid or material. In real life, this may or may not be constant because you know that the convection coefficient depends on the velocity of the fluid, the density, and all of that. That's a different thing we are not covering right now. We simply say that this is a limitation that really you have to enter a constant convection coefficient for the air or fluid surrounding your device. And then you specify the ambient temperature. Say, okay. So that's all you need to do. It's really the only thing you need to do is to say, okay, I want to couple the thermal, okay, and this is a liquid that which is applying a convection on the device, nothing else. So the simulator will automatically take all the thermal losses, namely the ohmic and core losses and so on and so forth, eddy losses, and apply them automatically. So let's see how you apply a coil. And again, it's not the subject today is not to a general presentation about the program. It's just mostly the thermal electro-thermal part of it. But just nevertheless, let's see how we could apply winding. So one coil. Okay, so you specify, for instance, if I want to specify this coil. Wait a minute, let me actually. I can isolate, thanks to SolidWorks makes it so easy to isolate because I'm working with this particular winding right now. I don't care about the others, so I say isolate and say winding. Okay, so this is one of the windings. You specify the AWG, and if you don't know it, you can specify the diameter of the wire. Okay, you could have a current driven or voltage driven. Current driven if you know the current flowing into your coil, so you just specify it. If you don't, if you only know the voltage, you could equally apply the voltage. Okay. Of course, we know that this is the coil, and we know the current has a direction, so we need to know how the current is going to flow. For that reason, we need to say entry port. So in this case, you say, okay, my entry port, select other, and say this is my entry port. So the current is going to flow clockwise in this case. And same as entry port, because this is a multiply connected, just a loop, so it's going to enter and exit exactly from the same phase. All right, then you have the number of turns and the current per turn, okay, whatever RMS current, and you have also the phase. In this particular case, we have a three-phase transformer, so each phase will have like 120-degree difference between the phases. So this one is 0, and the other one you can specify 120, and the other one 240. All right, that's all you need to do. So you could hide or show and say, okay. All right. So you could also do the same thing for the other windings. Okay. Then you mesh, and that's all. So let's go straight to the results. So this is my mesh. Okay. Now there are so many results here. I think I will explain briefly what each results folder indicated, what it means to your design. So first one is the results table. We call it results table because these are tabulated data, or lumped quantities, which something that you cannot represent on the mesh. You cannot say inductance on a mesh. Really, inductance is just the energy, related to the energy. So inductance in this case, I have 6 winding, therefore I'm going to have a 6x6 matrix. Okay? So you have self terms always higher than the neutral term. Neutral term is always negative. Similarly, you can see the impedance matrix, the current in each winding, or the voltage. So for instance, these are the secondary winding, and you can see there is an induced voltage in the secondary winding where we applied, if you look over here, we really applied no current for the secondary winding. Only the primary winding we applied current. So you can see now automatically that because of the magnetic circuit and because of this is an AC, and the current is going to induce voltage in the secondary winding. All right. Whereas you can look at flux linkage, you can look at losses. All right. So let me talk a little bit about losses. Okay. Now, so well, ohmic loss. Anytime you have a conductor, you're going to have ohmic loss or Joule effect, so to speak. Any losses, again, it could be related just to the current flowing. But if you have core loss, then in this case, we split the core loss to 3 components, being the eddy, hysteresis, and excess loss. And you can see those are all 0 except in the core material. Okay, so and you can see that the core loss is really the sum of 3 components. This table you can export it to a text file or an Excel sheet. All right, that's for the results table. Okay, and now these electrical parameters actually are post-processing quantities. We do not solve for inductance, we don't solve for impedance, we don't solve for force, we don't solve for torque. We really solve for the magnetic field. And from that, we obtain everything else. So in order to optimize your design, if you see a design parameter not quite as your intended design for that quantity, you probably want to see the reason. So for that reason, you want to look at the fields. So first one is the magnetic flux density. So you plot magnetic flux density, and you can plot any of the components. Okay, I could specify unit test or Gauss. You can specify Fringer vector, by the way, because these are vectors. So complication, yeah, it's true that we have less boundary conditions for magnetic, but we have to deal with vectors. Not only that, if you have an AC magnetic, we have to deal with complex vectors. So you're going to have really an imaginary part of your flux density. So let's just take fringe and take magnitude. You could also specify the phase, phase omega t. All right, say okay. All right, so this is your magnetic flux density distribution, and you could do several things with this. You could do a section clipping. Okay, so if I want one particular section, I can plot on section only. Okay, and you can see the skin effect that most of the field is on the skin, right? So inside, where this magnetostatic, most of the field is going to be inside. So this is called skin effect. So you could also add a second section, and the third, and the fourth, and fifth, and sixth, and all of them superimposed up to 6 sections. All together, you can you can visualize them, so you can actually see inside your device what's the values, and specifically if you have hot spots, you could also visualize that. So this is magnetic flux density. You could also do a vector plot. Okay, so if I do a vector plot, okay, so that's my vector plot. Okay, and my vector plot I could also animate as a function of omega t. So as omega t changes, as you can see now, it's going to shift from one. Okay. So again, the emphasis of this presentation is not really about the general capabilities of EMS. It's mostly about the thermal, electro-thermal part. So these are the electrical parameters. So you could look at the magnetic field and the related, magnetic and magnetic flux density. The applied current density, you probably want to look at it to make sure that you have the right circulation of the applied current density. This is the current that you applied, and these three winding. And again, if you animate, you're going to see that the phase is changing from one winding to another, and you can see now. There you go. Okay. Now, once you look at magnetic flux density, now you could now most of the interest for like this transformer design is the core, right? So I could simply isolate the core. Okay, and now I can take a look at the eddy current. Eddy current's flowing. I can do a vector plot, and you're going to see that it's flowing opposite to the applied current. Okay, so this is the eddy current, and you could also do a fringe plot. Okay, and you could then do an ISO clipping to be able to see where your maximum, and of course it's always on the skin. You'll be able to see where your maximum eddy current. That's, of course, is going to give you an indication. Wherever you have a maximum loss, you're going to have higher temperatures. So if you get high temperature somewhere in your model and you optimize or change that, you have to work around that. Either you change the material or the shape. We know that the sharp corners are a nightmare for eddy currents. They produce high field, hence high temperature. So what else? Okay, now let's look at the losses, because your temperature distribution is going to be exactly proportional to the losses, and you have all kinds of losses here. So you could plot your regular Joule effect ohmic loss, for instance. Okay, that's your regular ohmic loss, or you could plot some other type of losses, like let's say core loss. Okay. All right, so that's most of your core loss. And again, because so that's your core loss, and you could some situation maybe you want to see using the 2D tool, you want to see what is the loss, say, between this point and maybe this point over here. Okay, so you take a segment and you subdivide that segment to 20 points or 100 points, whatever, and then you can plot your loss. There you go. So now it's a 2D plot. You could zoom in or zoom out. You can track the values. Okay, 0 being 0.1 and 200 being second point segment. You could see the actual listing. So these are basically what per meter cubic. This is your core loss at different points. Okay, you could definitely print it, export it, save it, zoom in, zoom out. So it's a very versatile 2D plot. Okay. So now, once you plot your losses, then of course now you want to look at the temperature gradient and heat flux. So to do so, same idea, say 3D, and thanks God the temperature is not a vector, so just scalar quantity. This time I could do continuous, I could do lines, okay? And then I'm going to say okay. All right, so this is my temperature distribution. Okay, maybe let's do fringe first, then do the other type of the lines first. Okay, so this is my temperature distribution. Okay, it's K. I could change the unit to C. Okay. So now I know that the temperature could reach 108 degrees in the core material. Okay, and maybe even higher in the winding. So if I isolate and plot, okay, so it's 108. So maximum is really in the core material. Okay, so you can, same feature for all the plots is the you can do a section clipping on this one as well. So if I want to take a section and plot on section only, I can increase the number of, these are basically the temperature level. Okay, so as I move, you can see my temperature level. This is contour plot. Okay, so the highest is red, as you can see here. Okay, again, I can plot up to 6 sections or superimpose. So if I want a different section, superimpose, I could, or take this section instead. Okay. You can look at the temperature gradient, okay, in my model, or the heat flux. And all of these quantities, we have the same feature of the 2D, 3D plot, section clipping, so on and so forth. So all of them, they have that. So you could then study based on this, okay, how you alter or change your design if you don't reach your specs, or maybe you'll be happy with your design. It's just at the validation stage. Now, what are the limitations now? Now, will this replace your SolidWorks simulation? No, it's not going to replace SolidWorks simulation, where you have really a full-fledged, powerful thermal solver where you can take into effect the fluid part of it, the non-linearity, transient. But this is a quick way to check your design, validate your design, and be comfortable that you are not frying your transformer or your device at hand. So that's basically these are the capabilities of EMS. The advantage of this package again is really the integration, where you can switch back and forth between the electrical properties and thermal, okay, without actually needing to exit SolidWorks or open another program or import or export. Okay. Eventually, of course, you want a document to work, and we automate the documentation of your work. You can personalize your report by putting company logo, author, company date. And you can pick and choose which paragraph you want to include. So then you have the option between an HTML or Microsoft Word file. Say okay. Now it's now copying all the data, the input, all the parameters in a nicely formatted Word file. It's a file, it's a Word file, it's a regular Word file that you can edit. Okay, all of your results are there. They match the materials, load and restraint, coil information, results table. All of them are here. And last but not least, the field data, field plots. Of course, because it is a Word file, then you can simply generate a PDF file. Note that the Word file here, and again, this whole idea of philosophy of our company is really integration. So far, able to do the model, solve it, look at the results, and generate a Word file without exiting the SolidWorks. Okay, so now I can toggle between plot results while motion, if I have motion, in this case I don't, the model. So if you want to switch between them, you can look at the model or plot results or the report file, report tab, all inside the same environment, the SolidWorks environment. Okay. You may also ask, now, what about if I want to choose a different, maybe core loss for different material? Now, do I have to do the whole thing? And again, the answer is no, because you have this cloning your study, so I can copy my study. And now I have a copy of my study, the previous study is saved, so now I could just go and change whatever quantities I want, okay, and then run. Or better yet, you can generate many studies before you go home in the evening and run all studies. So simulator is going to go through each one of them, solve it, and when you come in the morning, you'll find and you'll be able to compare your results between different scenario and different studies. This is even without parameterization, of course. Parameterization is another topic because you can parameterize any model dimension in this. That's basically this is my talk today, and it's about the electro-thermal capability of EMS inside SolidWorks. And again, it's not really, it has limitations. It's just a steady state thermal, but it can give you a quick design check, especially if you are concerned about the heat generated by the core and ohmic losses. With that, I would like to open the floor for questions, and if you have any questions, I'll be happy to answer it.